Welcome back, participants, for this late afternoon lecture. This will be the third lecture by Professor Daniel Figueroa. It will be on primordial gravitational waves, or rather, as his title suggests, cosmological background of gravitational waves. Over to you, Dan.
Thank you very much. So welcome, everybody. Thanks for staying together to follow the third and last lecture. Let's continue now with our discussion on cosmological backgrounds from the early universe. We've covered so far a definition of gravitational waves, and then gravitational waves from inflation and from reheating. In the third lecture today, I'm going to focus on phase transitions and cosmic defects. But as we will see in a moment, phase transitions is actually a topic also related to preheating. So we are going to start by continuing with preheating before we jump into phase transitions in the thermal era. Now, what we saw yesterday is that preheating follows after inflation. And we study a couple of examples of what we can call scalar preheating, which is non-perturbative excitation effects of scalar fields. We saw that this gives rise to a very large production of gravitational waves, like stochastic backgrounds with very large amplitudes, and even possibly with multiple peaks if multiple preheat fields are involved. What we're going to see today is that in reality, a more realistic approach to preheating would typically require the inclusion of gauge fields, because our field theories are gauge theories. And I'm going to give you an example of this implemented in a scenario of multi-field hybrid preheating. So if you remember, we already saw briefly these equations, or this system of equations. This is a scenario of hybrid preheating where we are considering an inflaton, here referred as phi, which is coupled to some Higgs-like field, typically called waterfall field, but I'm going to refer to it as the Higgs-like field or just Higgs. This does not need to be the Higgs of the standard model. It's a Higgs-like field because it has a symmetry breaking potential pretty much as the Higgs of the standard model. So here, for instance, we have the coupling between the inflaton and the Higgs. And here we realize that in this mass here, in the dynamics of the Higgs, where we write the mass, there is the self-coupling of the Higgs, there is a vacuum expectation value, and there is the coupling, the same coupling here, but written in this more hidden manner, where we define a critical value of the inflaton as a function of the mass and the coupling. Okay. So this scenario, essentially the potential looks like this. Along this valley, the inflaton is inflating the universe. At some moment, the inflaton hits the critical value, this value here. And once it becomes smaller than such critical value, it turns negative square mass for the Higgs-like field. So the Higgs enjoys an instability. Okay, and why is that? Because essentially the effective potential from the point of view of the Higgs, as this becomes negative, so as the inflaton becomes smaller and smaller than the critical value, it's developing two symmetric vacua around the zero value of the Higgs. And of course, when I say two symmetric vacua, this doesn't mean that we are playing necessarily with a Z2 symmetry where the Higgs can only take -1 or +1 values. This is just the cut of a multidimensional Higgs manifold. Okay, but in any case, essentially what this gives you the idea is that this kind of preheating mechanism in reality corresponds to a phase transition, because there's going to be a spontaneous symmetry breaking of the Higgs-like field chi, since its effective potential develops naturally through interactions deeper minima towards which it's going to go actually exponentially fast due to the tachyonic instability. So it is a preheating scenario because there is a tachyonic exponential instability through tachyonic effects, so effective square mass negative, and it is a phase transition because we are actually spontaneously symmetry breaking the symmetry, originally holding the Higgs at 0. And now the Higgs will take a non-zero vacuum expectation value like this. Now, in order to make it more realistic, we are going to gauge this scenario. Unfortunately, just to confuse you a little bit, I realized that I exchanged the variables here by accident. So, well, now in this equation, chi is the inflaton and phi is the Higgs. I'm sorry about this. but I hope from the equations themselves you can see clearly what they represent. Here we have a gauge sector, say, let's be a billion gauge fields. In principle, these don't need to be those of the standard model, okay, because this is not the Higgs of the standard model. The Higgs guy is charged, no? So there's a gauge covariant derivative, and then there is the potential with the interaction between the inflaton and the Higgs, with the symmetry breaking potential of the Higgs, the interaction, and if you want some inflationary potential for the inflaton, which can take a different form than this simple mass term. This is irrelevant. So now that we have gauge fields in the game, which are directly coupled to the Higgs, it's immediate that if we are going to excite the Higgs through a tachyonic instability, because the scalar, the Higgs field is coupled to the gauge fields directly through the gauge covariant derivative, we are going to excite the gauge fields as well. Okay. So the dynamics of this system is a bit more complicated than previous systems, but typically if we choose the energy scale sufficiently low compared, for instance, to Gatt scale, then we can solve these equations just in Minkowski, because the time scale of the dynamics of the evolution of the fields, it's way faster than the Hubble scale. Sorry guys, just one confirmation. You see my screen, right? And everything. Is it because I don't see the sharing square here?
Yes, yes.
You see everything.
Is fine.
Everything is fine. Okay, thanks for the confirmation. Okay, so we're going to solve this system of equations in Minkowski. For simplicity, we choose a gauge also. So we take a temporal gauge. This amounts to solve the Higgs dynamics on the one hand with the covariant gauge derivatives in the form of this Laplacian here, the gauge field dynamics with a source given precisely by the scalar fields. Okay, and on top of this, of course, we will solve the dynamics of the inflaton too, of the singlet field. And together with the evolution of the field, we're going to solve in real time the wave equation of the tensor perturbation representing gravitational waves, including all terms in the source. So from singlet scalars, the inflaton, charge scalars, the Higgses, and gauge fields through electric and magnetic configurations. And we are going to do that, all of that in real time, to see what is the production of gravitational waves during the actual transition from Higgs expectation value 0 to Higgs expectation value different than 0. Okay, so there are new terms compared to the anisotropic stress transverse part I considered yesterday, which is the covariant part, the magnetic and electric parts. How does it look when we do these simulations? Here I'm plotting in a three-dimensional distribution of the amplitude of the Higgs field. And I don't put units here because I only want you to see the relative amplitude of the numbers. And what you can really tell immediately that as soon as we trigger the instability, since this instability corresponds to stochastic fluctuations, then stochastically we nucleate like bumps, quasi-spherical of the Higgs distribution, inside which the Higgs has a large amplitude compared to the surrounding media. These let me call them bubbles. They are unstable, so they grow in amplitude with the Higgs inside in amplitude. So here the legend is an order of magnitude bigger than in this plot, and they are also expanding because they are unstable. So eventually these bubbles are going to collide with each other, and well, that's going to release a lot of energy. But what I want you to see right now in this plot is that here, once we are fully at the collision of the bubbles of the Higgs, in between these red and white bubbles, red and white represents the highest value of the Higgs, there is some yellowish color, like in some elongated configurations. I don't know if you can really see by eye, because I don't know how good you see the colors of my screen, but to be more concrete, if we look at the gauge field, for instance, the magnetic, to make it gauge invariant, the observable we look at the magnetic field configuration. What we see is initially there are these bumps distributed all over the place, but they start taking a very well-defined shape. This shape corresponds to elongated objects, which are called cosmic strings. So what's going on, I'm asking here out loud, is that we are forming cosmic strings because I chose a symmetry breaking pattern such that there is a non-trivial topology, if you want, of the vacuum manifold that give rise to topological defects that are called cosmic strings. Now, since the second part of my lecture today is about topological defects, we are gonna postpone this and we are gonna focus only on the bubbles, okay? Right, so here I'm showing you now the matter spectra of a scalar degrees of freedom of the Higgs in particular, and vectors, meaning the gauge fields. So, for instance, here we see that the Higgs has a middle peak. Okay, this is the spectrum of the Higgs, just Higgs squared times some power of momentum, has a middle peak. This has to do with the tachyonic instability. So the location of this peak has to do with its tachyonic mass. And sometimes there is even an infrared peak, but today we are not going to discuss that because this really depends a lot on the details of your initial conditions and tuning of your initial condition. So it's not generic. On the other hand, there is one single peak for the magnetic field configuration. Here I'm plotting the spectrum of the magnetic field, so magnetic field squared times some power of momentum. And you see this middle peak of the Higgs and the magnetic field do not need to coincide. The reason is that the position, the location of the peak of the magnetic field that I'm plotting here separately really depends on the ratio of the gauge coupling between the gauge fields and the Higgs and the self-coupling of the Higgs itself. So altogether, you know, in this abelian Higgs scenario, there are many parameters. There is the tachyonic mass of the Higgs. There is the ratio of self-interaction of the Higgs to the coupling Higgs inflaton. There is the ratio of the gauge coupling of the gauge field to the Higgs to the self-interaction of the Higgs. And there are some other parameters depending on the model. Altogether, these parameters control, of course, the outcome of what's going to happen. So what I want you really to focus here is that the peak of the gauge fields, which is the novelty here, it's really controlled by the ratio of the gauge field mass to the Higgs mass. In other words, the ratio of the gauge coupling to the square root of the self-interaction coupling of the Higgs. So how does it look, the evolution of the gravitational wave spectrum at the time of production? Well, if the separation of gauge coupling from lambda it's not much, is of order 1, there is a single peak in the spectrum of gravitational waves at the end of the process. On the contrary, if the separation is of the order of 10, the peak of the gauge fields is pretty well separated from the middle peak of the scalar sector. So this means that these gravitational wave spectra are very interesting, very rich in information, because essentially they contain a series of peaks that are probing the strength of the couplings once again. So similarly to what we saw yesterday for the scalar sectors, now we see that in the moment we introduce a gauge sector, now we are sensitive to the gauge couplings and the scalar couplings altogether. Okay? And typical example of this spectra are going to have 2 peaks: middle peak from the Higgs instability, ultraviolet peak. I call it ultraviolet just because it's at higher momenta of the gauge fields. And depending on initial conditions, could be an infrared extra peak of the Higgs. But again, forget about that because it's even difficult to demonstrate that. So several peaks, probing couplings. It means, once again, the idea that we introduced yesterday, that we, in principle, can do particle coupling spectroscopy. If we were able to measure this background, imagine the power we would have, because we could do particle physics measurements, literally. Okay. How big is this background? Well, it can be rather large. Again, the omega gravitational wave spectrum today, the peak amplitude can be of the order 10 to minus 11, even slightly larger in certain choices. Unfortunately, again, like it happened yesterday, typically, if you want to sustain a very large amplitude like this, in this kind of multi-field reheating scenarios, you need a very high frequency, I'm afraid. I'm very unfortunate, there is no high frequency detectors, not with enough sensitivity. Okay, yeah. So what we are studying here is a purely theoretical case which shows the power of gravitational waves probing particle physics, but we still need to, some ingenious development of technology in order to probe high frequency gravitational waves. Okay, and you see, in summary, during...
Danny, this is Sriram here.
Yes, Sriram, please go ahead.
Hi, Danny. This is Sriram. Can I ask a question? This frequency being so high, is it essentially because you are talking about all the things happening during preheating? Unless it happens at an earlier epoch during inflation, it's unlikely to have at smaller frequencies. Am I correct to say that?
Let me put it this way. The reason why frequency is high is because these are high energy scale models of inflation, okay? And these are, I need them to be high energy scale models in order to have sufficiently large amplitude for the background of gravitational waves. In these scenarios, you could consider, for instance, this preheating transition at the electroweak scale. Nothing prevents you from having this scenario doing that. In that case, the frequency will be much lower within observable range of detectors, but the amplitude of the background would be absolutely negligible because it's controlled by the strength of the energy scale. So the problem is that there is this vicious game to play between the scale of energy scale which controls both some partially the amplitude and the location of the peak. You know, so this is the real problem. Right. In other scenarios of preheating, yeah, this is really the problem. So in reality, in this particular scenario, one could make a fine-tuning, but really extreme fine-tuning, in which if you take, for instance, the self-interaction of the Higgs to be 10 to minus 40, I think it is the value you need to take, but the BEF to make it GAT scale, okay? So effectively, you've reduced the energy scale of your system in such a way that you still can have sustainable amplitude of gravitational wave background, but you can shift it due to the smallness of the self-coupling of the Higgs to observable frequencies. But the problem is that that self-coupling is ridiculously tiny and unmotivated, and well, if one wants to live with it, yes, you can make a prediction, but it doesn't seem very expectable, no, or it doesn't seem very easy to expect such a thing, I think, from particle physics. Okay, so this is the problem, you know, that in order to make it within observable range of frequencies, you need to tune parameters to very, very small values in an ad hoc manner also, because you see, maintaining GAT scale in the BEF, but having the self-coupling to 10 to minus 40 is a bit contrived, in my opinion, you know. Okay, Thank you for the question, Sriram. There is a possibility for a monomial potential, so the kind of a scalar preheating I was showing you yesterday, that if you again separate the curvature of your potential from the height of your potential during inflation, you can play again to shift to lower frequencies your background, but it's very tuned, you know, it's very tuned and contrived. So I think it's much more likely, as we will see in a moment, that through a phase transition, for instance, in the thermal era, we can produce an observable background still with sizable amplitude. Now, to finish about preheating, so we've discussed scalar preheating, one example of gauge preheating. We see that there are always large peaks at high frequency, naturally. Just to mention, there is also fermion preheating, which also can give rise to large production of gravitational waves, even though not as large as the bosonic examples. I don't have enough time to cover everything, so if you want to have a look, there you have a couple of papers about fermionic preheating and gravitational wave production. Also, very interestingly, if you want to reheat into the standard model, or there are other effects other than just the power spectrum, maybe anisotropies, well, this can be worked out, but I leave you just with a couple of references of mine and for the people in case you want to have a look. All right, so we've discussed reheating through preheating scenarios. Now let me move on into phase transitions, but phase transitions not anymore through hybrid preheating, but through the thermal universe. No, so let's discuss thermal first-order phase transitions. Okay, so the actual core content of this third lecture deals more with these thermal phase transitions and with cosmic defects. So let's carry on. Okay, thermal first-order phase transitions. What is this about? Well, imagine we've successfully reheated the universe. The universe is in the thermal era, and there is a plasma of relativistic degrees of freedom driving the expansion of the universe. There's a certain temperature. This temperature is dropping all the time because the universe is expanding. And now let's consider an effective Higgs-like field again. This could be Higgs-like Higgs of the standard model, could be Higgs-like field of any extension of the standard model. Its effective potential, it's typically corrected from thermal corrections, and we normally or typically have the situation that when the temperature is sufficiently high, above a certain critical temperature of the theory, there is a single minimum and your Higgs is relaxed there in that minimum. But when the temperature drops below this critical temperature, which of course depends on your choice of theory, you may develop a deeper minimum, and hence you are going to break spontaneous the symmetry. This can happen through tunneling or through thermal fluctuations, really depends a lot on the scenario you consider. But in either case, the result is that in real space, you nucleate again bubbles. Here, the mechanism is different from the tachyonic instability I discussed before, but the result is very similar. At the end, you have bubbles where the Higgs has the true expectation value inside, or dynamically is arriving into that non-zero vacuum expectation value. And these bubbles are unstable because they have some pressure that is not balanced in their boundaries. So they expand and they collide. Now, if that happens, you can imagine, again, that we are going to produce a significant amount of gravitational waves. So these kind of first-order phase transitions, they are called first-order because there is, this barrier, okay, in the separation of minima, and therefore you can jump, you can make a finite jump of the Higgs amplitude from 0 into a finite value. And as you can imagine, this kind of configuration is going to release a lot of energy. And it's going to be a very anisotropic situation once bubbles collide. And just from the collision of the bubbles, from the bubble wall profiles, we are going to produce a lot of gravitational waves. But furthermore, because there is a fluid now, because we are in the thermal era and the fluid is coupled to the Higgs, you are going to set up like some waves. These are like waves of pressure in the fluid. Sorry, 1 second. So after the bubbles collide, because you are going to stir up the plasma, you are going to produce, I'm very sorry. You are going to produce like waves of pressure, and these waves of pressure, they are going to emit themselves gravitational waves. Furthermore, if there are gauge fields in the game, again, they are going to be stimulated, and perhaps if you produce so-called magnetohydrodynamical turbulence, they can contribute further to gravitational wave production. Of course, all of this can be captured technically. For instance, the wall profiles, you will introduce again the gradients of your field. For the sound waves, you can introduce a fluid dynamics describing the energy density, pressure density, and velocity of your fluid element. And for the gauge fields, you will introduce the previous anisotropic stress. All of these elements have to be taken together depending on your theory choice in order to understand the production of gravitational waves. So as you can imagine, it's really complicated. It becomes really complicated. However, let's be simple in order to understand the basics. And the first observation is that this is a causal source, which is operating with dynamics that, of course, cannot produce anything at super horizon scales, because this is a causal mechanism. So essentially, the frequency of whatever the final background of gravitational waves here is going to be a fraction of the Hubble scale, where this, of the Hubble radius, if you want, where this epsilon has to be smaller than 1, so that the frequency is bigger than the Hubble rate. Okay? Now, the frequency today is just the redshifting, it is the frequency at the time of emission, this one, redshifted till today, taking into account the expansion history. And since we are already in the thermal era, this can be written in a very simple manner in this parametric formula, which essentially tell us that everything depends on the energy scale, the temperature at which the phase transition occurs. And now it happens that for standard values of epsilon, which is typically smaller than 1, as I said, and typically around 10 to minus 2, 10 to minus 3, etc. For these values, it turns out that for the temperatures or energy scales around the electroweak scale, this background is going to be peak at the millihertz. And why is that relevant? It is relevant because that's the peak frequency of the will-be first observatory of gravitational wave detection in space, LISA. Okay, so LISA, by chance, it's a natural experiment to measure the electroweak physics in the early universe. Now, of course, what determines this epsilon in a first-order phase transition? This depends on the microphysics of your system. Essentially, initially you have your bubbles collide, and this takes a time scale. We call it typically beta to -1, and they propagate at a given velocity, which has to do with the friction with the plasma. So at the end of the day, there is a radius upon collision of the bubbles. And essentially, this epsilon is mostly determined by the ratio of the time scales of the phase transition to the Hubble time in the case of bubble collision, and the ratio of the radius, which depends on the velocity and other aspects, to the Hubble radius for the sound waves and the possible development of turbulence. Let me give you some brief description of how the formulas go on, but I'm not going to enter into the full detail because this would take a whole lecture of 2 hours to discuss how to build the formulas of gravitational wave spectrum from phase transitions. So we know already that the frequency is is controlled in a very simple manner by the temperature. We know that this epsilon parameter is also, at least in the simplest cases, controlled essentially by the beta and the radius, which depends on the velocity. So essentially, we see already 3 parameters here that control the whole effect. Beta, remember the inverse of which is the time scale of the phase transition, at least of the collision time. Velocity of propagation of the bubbles, which is controlled by the microphysical interaction of the bubble wall with the plasma, and energy scale of the symmetry breaking. If we put all of these together, essentially we can work out in a very simple manner that the spectrum today of gravitational waves is basically controlled or suppressed by the ratio of the energy density of radiation to the critical energy density today. The epsilon parameter again enters quadratically, controlling the final amplitude, and then the ratio of the energy density of the stress tensor creating the gravitational waves to the total energy density. Okay, where this stress tensor has multiple contributions. Remember, there is collisions or gradients, but there is also sound waves or turbulence. Altogether, we can add a couple of more parameters. Alpha, the ratio of the vacuum energy inside the bubbles to the radiation fluid outside, or kappa, the ratio of the kinetic energy of the walls to the vacuum energy. As I said, I'm being very simplistic, and in reality, you have to take into account hydrodynamical effects and possibly turbulence, the development of turbulence. And this is not captured by these basic formulas. There are other formulas and other considerations. But as I said, I'm not going to dwell into the technicalities of that because it would take too long. I'm rather going to give you an overview of how people are doing this nowadays. So first of all, the whole business of bubble collisions started with analytical computations in the, well, it was first predicted in the 80s by Witten, actually, by Edward Witten. Then it was continued in the early 90s by some seminal papers with analytical computations. But at the end of the day, people turn into numerical simulations because there are many regimes that you want to capture, and it's not really easy to do it analytically at all. And it's simpler in some sense to go into numerics. Then the whole business of sound waves, waves of pressure, started only not even 10 years ago. Actually, it was started by some of my closest collaborators. And it all went numerical from the beginning because these sound wave predictions are based on simulations of a scalar field coupled to fluid dynamics. There's some analytical considerations, of course, but at the end of the day, the status of the art is driven by these very complicated simulations. And then considerations of turbulence, again, were initially evaluated analytically for many years, actually, there's been, several developments in this analytics. But at the end, people have jumped finally also into numerical simulations, again, considering fluid dynamics in particular. So, as you see, this business of gravitational waves from phase transition is very complicated, and it's a whole world by itself. It's one of the hot topics nowadays in gravitational wave background from early universe, and is one very interesting to jump in because for the following reasons. It represents a direct connection between particle physics, the physics describing the phase transition based on high energy physics modeling, and cosmology. And it represents a new way to probe beyond the standard model physics in a complementary manner to colliders. In particular, LISA, the experiment LISA, once it flies, it'll be a natural detector for the electroweak phase transition in beyond the standard model scenarios, just given what is the natural frequency of LISA. Whereas in other scenarios, let's say high energy scale scenarios, the range of frequencies actually can be much higher, depending on the temperature, and we can be in the megahertz, gigahertz, terahertz, etc. For where, unfortunately, there is no much of detectors, as I said. But maybe the idea with these results is to bring up the experimental community to understand that there is a lot of at stake, because if we want to probe eventually really high energy physics above the scales we can reach with accelerators, we may want to consider developing technology in these high frequency ranges. How does it look? The spectra, the typical example of these phase transitions. Here I show you a paradigmatic example where there are three contributions. There is a contribution from analytical considerations of MHD turbulence. There is, in green, the contribution from sound waves, which is typically larger than the contribution from wall collisions. You see, these typical spectra have some infrared tails and UV tails. You have to add them up incoherently, typically, but this really depends on the scenario. And then you have an envelope, in this case, that has, for instance, two peak structure. So now this is not a spectroscopy of couplings. This is simply contribution from different elements contributing to generating gravitational waves. So a standard prediction from these phase transitions is that this spectra has typically a single peak or two peaks, depending on what source dominates. Now, what's the most relevant aspect of this plot? Perhaps it's not so much to think of whether it has one peak or two peaks. The really very relevant aspect, in my opinion, is that here, once again, we are talking about direct detection of gravitational wave background from the early universe. So this is a reality, guys. Maybe it's not happening now, maybe it's happening in the next decade, in the 30s. That's when LISA will fly and other experiments like Einstein telescope and others. But this is going to be happening. Doesn't mean that we are going to be necessarily measuring stochastic backgrounds from the early universe, but it certainly gives a very good perspective to think, to realize that we are discussing about the possibility to possibly measure these backgrounds. Okay. In other words, that this is not just science fiction. This red curve here at the back is the sensitivity, projected sensitivity of LISA. Well, in reality, it has suffered some modifications, so it's something in between the pink and the red one. But the point is that within the reach of certain experiments, in the next 10, 20 years, we are going to be directly probing the early universe through these gravitational wave backgrounds. If these gravitational wave backgrounds exist, which depends very much on what's the physics of the early universe, we could make a direct measurement, and this would be an absolute revolution. Okay, we would be measuring directly, seeing directly the early universe. If we don't measure nothing, after a number of years measuring, accumulating data, we will put stringent constraints into many particle physics theories. Okay, so I think I've already said now that LISA is a very important experiment because it can be sensitive to energy scales around the electroweak scale. For that, of course, you need to be in beyond the standard model, because otherwise in the standard model itself, you don't produce a first order phase transition. Okay, the transition, the electroweak symmetry breaking in the standard model is not first order. But it's very easy to build BSM extensions of the standard model that contain degrees of freedom that turn into a first order phase transition, the electroweak symmetry breaking, and also in dark sectors or considerations really beyond standard field theory, like considering extra dimensions, for instance, we can go beyond the electroweak phase transition and simply think of dark transitions, which we don't know. This depends on the model, how they are connected to the standard model. But the point is, since they emit gravitational waves, because everything gravitates, we could see perhaps a signature of a, a dark sector happening at the right scales in the right experiment. And the plethora of experiments that are expected for the next 10 to 20 years is immense, and it's getting better every day. There are proposals almost every month. So can we really detect then a first order phase transition from the thermal era? Well, LISA, which is the most solid perhaps experiment put over the table in order to do this, can potentially, but of course the LHC is going to put pressure into some of the BSM scenarios that give rise to a signal. So by when LISA flies, maybe only a subset of these scenarios will be allowed. Assuming LHC does not rule out models before LISA, yes, we can still detect constraint a significant fraction of parameter space. Of course, the predictions depend on many assumptions, particularly in the case of some waves, since these are not very well controlled under analytical evaluation. So there is always the doubt to what extent our modeling numerical is fully correct. And even if we detect one of these backgrounds, there's always the question of, okay, we are going to infer alpha and beta and maybe a couple more of parameters, but there are going to be many theories degenerated among themselves producing these parameters. So it's not going to be univocal. So maybe we will need to cross-correlate this kind of detection with something else. Okay. And well, I think I finished here the phase transitions in the thermal era and the phase transitions in general, because we covered tachyonic effects in hybrid preheating, which is a phase transition, and first order phase transition in the thermal era through nucleation of bubbles, either through tunneling or thermal fluctuations. Now we should enter into cosmic defects. We will see that there are actually two contributions to cosmic defect networks. One is the so-called, or that I call myself, the irreducible background from a cosmic defect network. And another one is a very specific background, but maybe the most relevant one, from string networks, which comes from loops. Then I'm going to continue. So as I was saying before the small break, last part of this presentation now is going to be focused on cosmic defects. I'm going to start by what I call irreducible background of gravitational waves, which is not at all the historical, the background discovered historically first. Now, cosmic defects are what? These are a possible aftermath product of a phase transition. They were pioneered by Tom Keeble, that was the person who introduced them already in the literature, in the cosmological literature, more than 40 years ago. Because he understood that under certain circumstances, in spontaneously broken theories, domain structures that are called cosmic defects may appear in the universe. So what is this about? Well, imagine you have a situation like a kind of phase transitions we've been considering, where there is an initial group of symmetry G, and you break the symmetry spontaneously into a subset H. So there is still a symmetry H, but it's smaller than the original one. And there is a vacuum manifold corresponding to the coset between these two groups. And essentially, depending on the properties of this vacuum manifold, this is what Keeble understood, you can have one type or another of cosmic defects. Let's see this in detail. So what does it mean, really, a cosmic defect? Well, think of this Mexican hat potential that represents the symmetry breaking potential, no, of phase transition, and the Higgs, the arrow here represents the amplitude of your Higgs-like field. Initially it was at 0 with 0 expectation value, but now it has a BEF represented by the length of the arrow, but in which direction it points within the vacuum manifold is completely arbitrary. As a consequence, in the universe, there are going to be places in the universe where the arrow is aligned into a certain direction, the arrow is aligned into another direction elsewhere, and so on and so forth. So the question is, what happens in the boundaries of these regions? This is what Kibble addressed. And in order to understand this, let's consider maybe effective potential. So we take a Mexican hat potential for a symmetry breaking pattern of a Higgs-like field and consider some interactions of these Higgs, maybe through thermal corrections or through inflaton interactions, for instance, in the case of hybrid preheating. Now imagine the interactions trigger the phase transition and the Higgs develops vacua, a new set of vacua, no, which is the vacuum manifold compared to the single vacuum it had originally before the phase transition. So the Higgs is pointing in two different directions within this vacuum manifold in these four corners of a spatial location in space. And I place together these vectors here at the origin of my system of coordinates. And what happens that if the Higgs is taking this kind of configuration in this particular corner, it has to take a continuous configuration to begin with. So essentially, the vector has to rotate within this vacuum manifold. Furthermore, if the amplitude of the vector is non-zero, this means that as we approach really the center of this configuration, the Higgs is necessarily forced to go to 0 to climb up this potential, because otherwise it could not be continuous. How could you extrapolate, how could you interpolate, sorry, the Higgs BEF pointing in this direction in the vacuum manifold to the Higgs pointing in this other direction in the vacuum manifold, which are completely opposite? The only way is to reduce the amplitude of the Higgs BEF, so the Higgs climbs here until it goes to 0, and then it goes in this other direction. And this is why cosmic defects are so special, because they correspond to the configurations of the field, where the field does this very special aspect, not to match in a continuous manner the distribution of its amplitude everywhere. And depending on the properties of the microphysics of your scenario, what you can have is cosmic strings. We already saw one example in the simulations I was showing before. You could have monopoles. Gauge monopoles are forbidden actually, so it could only be global monopoles in principle. Or you could have textures which are not isolated objects, but correspond to large gradients of field configurations. All of this depends on the microphysics, as I said, but depending on this microphysics, then you can have one type of cosmic defect or another. So here we are in the previous example. This is a phase transition, the breaking of U1 in a hybrid preheating scenario. Through tachyonic instability. It doesn't really matter the mechanism to break the symmetry. We create bubbles, they appear randomly in places, they expand, collide, and as we noticed before, there are in between the bubbles some yellow segments here, which imply the field taking a much lower amplitude. So essentially, if I now plot three-dimensionally the values of the Higgs, where the amplitude of the Higgs is very small compared to the BEF, this corresponds to these elongated configurations, the Higgs strings, okay? Where the Higgs is minimum in amplitude, but the potential energy is maximum because it's kind of at the top of its Mexican hat potential. At the same time, if I look for the direction in the vacuum manifold, which is two-dimensional here the Higgs is a complex field with real and imaginary part, and I plotted with colors the phase of this direction in the vacuum manifold, what we see is that around a string, we see the 2 pi rotation expected of the Higgs configuration. So essentially, the physics happens as predicted by Kibble, and this can be simulated and well seen. If we look at the magnetic field configuration, as we already saw before, they follow again the same concentrations, special points in space where the Higgs is minimum and gauge energy is maximum. Magnetic energy is actually maximum. So what kind of cosmic defects you have? These range from domain walls to cosmic strings to monopoles to non-topological. It really depends on the microphysics, on your choice of a scenario, the symmetry breaking pattern you have, the topology, if you want, the homotopy groups is the technical word of the vacuum manifold. Okay, but we are not going to enter into those technical details. You are, of course, welcome to ask later on if you want. What is more relevant for me is for you to focus on the fact that due to the fact that this is microphysics constrained by causality, there's going to be naturally a correlation length between the different defects you may produce after a phase transition. And this correlation length, of course, can only be at maximum a fraction of the Hubble scale, which represents the causality scale in the standard expansion history of the universe way after inflection. Okay? Keeble, with his great insight, understood that this fraction is actually of the same order. So the fraction is of order 1. It's constant, first of all, and it's of order 1. So in other words, the correlation length typically separating the defects or characterizing the spatial scale is tracking the Hubble radius as the universe expands. Or in other words, I could typically plot, quantities of any defect network in terms of comoving momenta normalized to the comoving Hubble rate. So k times t or k over curly h, where t is conformal time, because we know the typical scale is going to be with this variable around 1. Okay, because essentially we are tracking the Hubble scale. So essentially, physically, pictorially, if you want, this is what's going on. As the universe expands, the Hubble radius grows, and the distribution of defects scales, and this is called the scaling distribution, scales with the growth of the Hubble scale. Now, we know that gravitational waves are produced by gradients of fields, electric and magnetic field configurations. And these cosmic defects, for instance, think of strings, correspond to very sharp gradients, very acute gradients with huge concentrations of energy inside the tube, okay, and a certain profile in the boundary between the tube of energy and the surrounding field. And this means that there's going to be a non-trivial transverse traceless part of these configurations, and plus these are relativistic guys, so essentially they are a natural source of gravitational waves. Now, how to compute the spectrum of gravitational waves from a whole network? Well, first we need to understand that we need to construct or to obtain this object. This object is called the unequal time correlator. So it's the statistical correlator of two copies of the transverse traceless part of the energy momentum tensor of the defects. And its amplitude is called the unequal time correlator, or UTC for short. And why is it relevant to know this object? Because if you can compute it, there is a master formula in when you study the spectrum of gravitational waves in general from a stochastic source that tell you that the energy density spectrum from a stochastic source is given by a double time integral over expansion history times some Green function times this unequal time correlator. Okay. All of this comes from the famous wave equation sourced by the anisotropic stress transverse traceless part. It's not just magic. So from there, you can build up that the spectrum has this form. This means that if I know this object, I can predict what is the energy density spectrum of gravitational waves. But because my network is in scaling, I actually don't even need to know exactly what is this object, but I can predict in scaling, as long as the network is in scaling, what is the functional form, the dependence on scale. And essentially, it must depend on scales through this dimensionless combination, k times t prime, okay? These are different times of the correlator. And this has to come like that precisely because of the scaling property, that the scales are always following if you want the inverse of the scale of time. And due to dimensional considerations, then I have to write this square root of product of times here and the BEF to the fourth here. So now if I know the scaling form, I can plug it here. Look that there is this square root of times. And remember that in radiation domination, in conformal time, a scale factor is linear in time. So essentially, this time integration, now I know how to do it. And what happens is that if I introduce these dimensionless variables, k times time, it happens that the k to the 3 power I had here, which was the scale dependence I was having together with this cosine here, or together with this unequal time correlator, I can introduce it inside the integral, change variables to these dimensionless variables, and voila, suddenly this integration becomes a number. It becomes a dimensionless number. So essentially, I've made disappear the scale. So in other words, what we are saying here is that the spectrum of gravitational wave today of any network of cosmic defects that is in a scaling, as it has to be a valid network, a viable network of cosmic defects, it necessarily emits, just during the scaling dynamics, a scale invariant background of energy density of gravitational waves, the amplitude of which is controlled by the BEF, the vacuum expectation value, and the functional form of the unequal time correlator, which you plug in this integral that you have to do numerically. Of course, the difficulty of this is to get what is this unequal time correlator, no? Which typically can only be done from numerical simulations. But in any case, the amazing power of this prediction is that for every kind of phase transition, no matter first order, second order, or something else, and for any type of cosmic defects, no matter topological or non-topological, if these defects become a viable network of defects in scaling, we do predict here that there should be a scale invariant background. Furthermore, that scale invariance, it actually has to do only with the modes emitted during radiation domination. Remember, I used the scale factor during radiation domination. If I take into account the whole evolution of the universe, radiation domination and matter domination with later on dark energy, the full spectrum at the end has two contributions, the constant part from radiation domination and another scale-dependent part from matter domination. The coefficients are given by these integrals. I don't care about the details of these mathematics. I don't want to show you that. Just want to show you that the universal form we expect is this one. It has a plateau. This is the amplitude of the plateau of the spectrum of energy density of gravitational waves versus frequency today. The amplitude depends on the vacuum expectation value, so the energy scale of the phase transition. And it has this feature, which has to do with this scale-dependent part, but this feature is always peak at the quality scale, which is very, very low for a point of view of direct detection gravitational wave detectors. So LISA, LIGO, ET, PTAs, whatever you want, are never going to prove this. So in reality, we only care about this amplitude. Unfortunately, it's still not very large. And it's very unlikely we will see this amplitude with direct detection experiments, but it's a very nice prediction because it mimics to some extent the prediction from inflation, and it actually predicts a higher amplitude for the same energy scale. Now, this is a hot topic, and there are recently other works for the first time, actually, because so far it was me and collaborators working on that topic, mostly, but now there are recent works on gravitational waves from global string networks. And I got to say that they don't agree with our prediction of a scale invariance. They rather make other predictions which enhance the amplitude of the gravitational wave background compared to ours, and they have some tilt. The reason why they don't agree is because they introduce a number of ingredients different than the ones we are considering. And of course, the question is who is right, who is wrong, or if any of us, you know. So this is a hot topic because it can be used to prove the gravitational wave background from a network of axion strings, which is expected in axion dark matter scenarios. So, well, there is now competition of several groups, which I really welcome because it means that we need to understand better, and it's very difficult to make this understanding, of course, what is the ultimate shape of this stochastic background of gravitational waves. What is this purely a scaling argument, as we are saying, or there are, for instance, log deviations to this scaling as the ICTP group claim, or other aspects that, for instance, this group in the US claims. I'm not going to dwell more on the details here. Again, if you want to ask about it in the turn of questions, I'm happy to discuss about that. Now, finally, we go actually into what is the historical prediction of gravitational wave background from cosmic defects, which only apply to string networks, and only apply to the case of cosmic strings, because in that case, and only in that case, there is an extra emission of gravitational waves besides the scaling dynamics of the network, thanks to the very nice property of cosmic string networks, which is that they intercommutate, which means that they chop off loops as the network evolves. With the long strings, they can self-interact themselves, or they can cross with other strings, and they produce loops. These loops are typically smaller than the Hubble scale. They have a lot of tension, all the energy accumulated in the fields there, and they naturally want to vibrate, oscillate, and in doing so, they emit gravitational waves. And this is actually what historically was predicted, as you see, 40 years ago by Vilenkin in a seminal paper. So I call it extra only in comparison to the fact that any network emits gravitational waves. The one of cosmic strings from the loop distribution emits another channel of gravitational waves. Any cosmic string loop that you produce of a given length L is going to oscillate under its tension, and in doing so, it's going to emit gravitational waves in a series of harmonics. There is a whole formalism that Vilenkin pioneered, and then together with him, other people in the middle late 80s, and later on it's been refined by multiple authors. And essentially, at the end of the day, what it says, this formalism, is that the energy density spectrum of gravitational waves from any network of cosmic strings comes or is modulated, is given by the tension here, the gravitational coupling, of course. Then there is the expansion history to take into account, because you have to accumulate the emission from the loops at every moment in cosmic history. Then you have to integrate over the distribution of these loops as a function of length. There is a loop number density function. And finally, you have to take into account what's the power emitted by any of these loops, which actually depends on the features that the loops have, whether they have kinks or they have cusps. And depending on that, they have, or other aspects actually, they have a different exponent here in this power law behavior. Putting all together, this is how typically it looks, the background. Here I'm plotting again the omega gravitational wave spectrum today versus frequency today. And it has a plateau part corresponding to the modes emitting during radiation domination, and it has a peak corresponding to the modes emitted during matter domination or dark energy. It's very similar to the spectrum I show from scaling, but it's very different in amplitude. And I will show you that in a moment. Depending on the size of the loops, the shape of the spectrum can be shifted. However, I've got to say that the biggest simulations to date of Nambu-Goto strings, okay, of infinitely thin strings, these are from the Boston-Bilbao group. They essentially point to a fundamental scale, which is the loops at birth are of the order of a tenth of the Hubble scale. So essentially, if you really privilege this scale and you take at face value the results from these simulations, then this favors actually to have the highest possible amplitude of the stochastic background. Unfortunately, well, there is the Boston group and there is a European group that they disagree pretty much in the restriction of the loop number density. And depending on what loop number density you plug in your master formula, you produce a shape or another. All of them have a plateau in high frequencies, and they have an infrared tail scaling as some k to the 3 power, if I remember correctly. But in between, you see they have a different shape. Now, they don't agree, the two groups, and of course, we need maybe more simulations or more analysis in order to disentangle, what is the best answer. Luckily, both predictions determine that the best tension you can prove ultimately is in units of Planck mass, g mu, 10 to minus 17. which is an amazing expectation, for instance, for LISA, 10 to minus 17 for LISA. How amazing is this? Well, let me show you for comparison. Current bounds on G mu, so on the tension measured on gravitational units from the CMB is 10 to minus 7. So LISA is going to be able to improve of 10 orders of magnitude. Current bounds from PTA are 10 to minus 11. So this means that we could improve 6 orders of magnitude with LISA. In the future, at the best, PTAs could measure down to 10 to minus 14. So still LISA could measure 3 orders of magnitude better. Of course, there is the possibility that PTA, maybe, probably you've heard of the claim by Nanograph that they've measured a stochastic signal, but stochastic noise, but they don't know what it is. No, there is no claim that's a gravitational wave background, so nobody should confuse it yet with that. But there is the possibility that the first measurement of a stochastic background could be around the corner. If that gets confirmed this year in the next round of analysis of Nanograph, we should really then try to investigate and understand whether that's compatible, for instance, with the prediction from cosmic strings. Or most likely, this is what many people will expect, it's probably the expected background from supermassive black holes, but to be discovered and hopefully this year. So finally, just a comparison, the shapes are very similar between the irreducible emission from the scaling properties of the network and from the loops, but the shape look similar by eye, but if you look at the amplitude, the scale for the same BEF, the prediction from cosmic string loops is actually much larger for the same BEF than the one from the scaling network. So the chances to really discover the presence of cosmic defects in the universe through stochastic background comes only or mostly from the prediction from the loop distributions. And this is why it's so important that in the next years, this discrepancy between the two groups about the loop number density could be clarified further. And with this, I believe I conclude. I think I'm even a bit ahead of time, I believe. But okay, we can give some margin for a few questions before the break, or I can have more time for lunch. So let me just give you general overview. You see, inflation cures the hot Big Bang problems. It generates naturally the initial conditions of the universe. This is what you saw in the lectures by Kinney, in particular primordial perturbation, scalar and tensors. We were concerned about the tensors because they are a stochastic background. The flexibility of inflation allows you for many ingredients, for adding many ingredients, and you can enhance the prediction from inflation. You can produce a large background of gravitational waves from preheating, and then there can be phase transitions that also produce their own background of gravitational waves, or cosmic defects that have two components of gravitational wave backgrounds. So with this, I think I've covered in a very general manner the whole picture of stochastic gravitational wave backgrounds from the early universe. This is the summary of the topics we've covered. And just to conclude very fast, what we've discussed in this lecture is that, you see, there are gravitational waves from inflation, but the standard prediction can only be searched in the CMB. We didn't discuss this in detail, we only mentioned it, but it's true, there is an intensive search for the vacuum background of gravitational waves from inflation at the CMB. And if you add extra ingredients, you can enhance gravitational waves. Whereas in preheating, very naturally, you produce a high amplitude, but typically at high frequencies. In phase transitions, the electroweak phase transition in BSM embeddings, it's observable within LISA. And for cosmic defects, gut energy scale cosmic defects or large energy scales, they are significantly detectable within LISA and other future experiments coming. But it's up to the future to see whether we will detect them or not. If you want to introduce yourself more at the technical level, here is some propaganda about the review I have myself with my close collaborator, Chiara Caprini. It's one of the leaders of the LISA experiment. And I think we covered here, at least in 2018, the plethora of backgrounds of gravitational waves from the early universe. And finally, last word, a piece of propaganda is that, as you've noticed, it's becoming more and more important in order for you to make predictions on gravitational wave backgrounds, to do numerical simulations. And for that, we've created a software very, very flexible. This is really the result of many years of work in my life, 10 years. And it's a very versatile platform that you can use to simulate cosmic strings, gravitational wave emission, nonlinear dynamics, and essentially whatever you want in reality. We're gonna provide a gravitational wave module in about 1-2 months. It's almost ready. And in order for you to learn how to use the software, because it's maybe not the simplest thing to learn, we are going to organize a school in Valencia. Hopefully, if the pandemic allows for it, who knows what's the situation by summer and autumn this year. But we're going to organize a school that we are going to coordinate with a number of institutes or universities worldwide, so that many people, maybe senior researchers or students or postdocs who want to learn this, will have the chance to learn it directly from us that we wrote the code. Okay, and with that, I really thank you for your attention. Thank you very much.
Thank you.
And now I've really finished. Thanks, Robert.
So there were a couple of questions.
There were a couple of
one I noticed Robert has answered. Are there any references for generation of gravitational waves from MHD turbulence?
Yes. Actually, I mentioned them I put them in the presentation, which I hope you still see. Of course, I can elaborate a bit more fine, but the basic ones, I think you have them in the presentation. So you see for gravitational wave production from MHD turbulence effects, you have these papers, and then there is this other paper for numerics. So following these names and the dates, you can definitely find these papers in archive. This person, please try to find them, or if you don't find them, let me know and I give you the explicit archive numbers, of course, if you prefer. Since I understand, Sriram, that we will... Sorry?
Sorry, go ahead. I was just reading out the next question.
Okay. No, I was going to ask you a question. I understand you are going to pass them the transparencies, right? So they will have access to this information.
I will write to, I will request ICTS to write to all the lecturers and get the slides for the individual lecturers, and we will make them available.
Okay, because there is a number of students in the Slack channel that are asking me actually for the transparencies. So I hope this answers that. Okay, the transparency will go to you guys. Just be patient and it will arrive.
We'll make it available on the website maybe, and I will request ICTS to write to the participants as well.
Excellent. Yeah. Okay. So, what else? Did you answer?
The next question is, sorry. The next question is, if LISA detects gravitational waves of frequencies that can be attributed to multiple early universe sources, how can we determine which is the biggest contributor?
That's one of the $1 million questions we are trying to address in the collaboration, because it's really a very complicated problem, since the LISA band is going to be crowded of signals, not only stochastic signals possibly from the early universe, but also stochastic signal from unresolved binaries that cannot be resolved individually, and also a plethora of individual signals from binaries that they can be resolved. Okay, so this is one of the most challenging problems of the LISA detector, and for that matter of any other detector in those with those capabilities that will be coming in the next years. And we are developing techniques to separate signals based on properties of these signals. Basic properties is what is the shape of the spectrum, but other properties could be what is their annual modulation. Other properties could be, well, whether, for instance, there are extra polarizations in modified gravity. Okay, this could be a fingerprint. Other properties could be whether they are non-Gaussian, but this is extremely difficult to prove for most of these backgrounds. To be honest, I would not really consider that. And yeah, that's it. There is no clear answer right now because this is work in progress. And we are clearly aware of the problem that, you know, we are going to have a stochastic noise. That's what LISA gives us. And we have to disentangle a number of sources from there. And it's not going to be easy. But there is good perspective. There is good perspective that if there is a primordial signal, which is not very, very suppressed compared to the stochastic background from unresolved binaries, from unresolved solar mass, astrophysical origin binaries that LIGO is measuring, for instance, there is a good chance with the techniques we are using already, predicting, that we'll be able to separate the components and measure that there is a primordial background. Now, the problem is once we measure the primordial background, imagine we see a single power law or we see a single bump spectrum. So to determine what's the physics behind that, we are going to need more information. The only thing we'll be able to do with that is to really rule out many other scenarios that don't give those predictions, and then isolate the parameter space of the scenarios that give rise to those predictions. But it's going to take more time, I'm afraid, eventually to be capable of determining what's the physics originating this background. We will need to do cross correlations with different experiments for sure. And we will need to not only gravitational wave experiment, but possibly other type of experiments, like cross-correlating with the CMB. It's a whole topic of discussion, of hot discussion in the community working in developing the techniques, the pipelines for detection of stochastic gravitational wave backgrounds for the coming experiments.
There is a question from Robert. Robert, please unmute yourself and speak.
Yes. Can you explain again the spectrum from cosmic strings at the very low frequency end? So from loops which are produced in the matter era.
You mean from loops, no? Not from the scaling network,
actually,
right?
Maybe for both.
Okay, sure. So when we only consider the long strings, let's say, no, in the network, so not the loops, the crucial element we need to predict what is the shape of the spectrum of a stochastic source, no matter whether this source is a cosmic defect network made of strings, made of something else, or is phase transition, okay? This is a generic formula for energy density spectrum of a stochastic source. And a stochastic source is stochastic because it's characterized by this unequal time correlator, which characterize these statistical properties, right? So now, because we are in a scaling with a network of, say, cosmic strings, we can predict this functional form. This is what this scaling implies that the unequal time correlator should be in this form. And because of this form, we are forced to take in scaling, then we have this particular isolated square root of powers of t. Oh, this is conformal time, okay? Now, if I plug in the prediction of the energy density spectrum during radiation domination, I have to put here linear time for the scale factor, which means that this will cancel out the square root, and I will have a square root here above the T1, T2 here. So in total, I will have dt1, dt2, a square root of T1, T2. And if I introduce k to the 3, and I make this dimensionless combination, this is what I'm left with. And this is the scale invariant part. But now you're asking me for the matter domination. So in matter domination, I could do the same exercise. I have the same form here. Of course, there is a different amplitude because this comes from the evolution of the defects during matter domination, but the same argument still applies because it's in scaling. And here I would plug in T to the 2, T1 to the 2, T2 to the 2, because that's the prediction of the scale factor in matter domination, in full matter domination. Okay, and if you were to do that, what happens is here I will have T1 to the 2, T2 to the 2. So I would not cancel out exactly this square root. I will have T1, T2 to the 3/2, and therefore I could not absorb exactly the K to the 3 here, and I'm forced to be left with a K dependence here. So I managed to write down a scale independent integral here at the expenses of isolating out what is the scale dependence outside. Now the question is, when does this apply? This apply for when the network of cosmic strings is entering into the matter domination, which of course in terms of time, this might look, in terms of time for us, no humans, little beings on Earth, this look like very far in the past in the universe. But in terms of scales of the expansion of the universe ever since decoupling and equality has only expanded a factor 1,000. Whereas during radiation domination, it expanded many more orders of magnitude. And this is why, once I start hitting the scales corresponding to equality, this corresponds to really cosmological scales of very, very low frequencies. And this is why I see the bump always at low frequencies.
So the rise that you have, if you come from the high frequency end, is due to the fact that the matter F is larger than the radiation F. And then the decrease, even at smaller frequencies, is then due to the scaling of the FUM term.
Yeah, this decrease, if you mean this tail, infrared tail that goes down, this is...
Yeah, the infrared tail is given by the K equality over K square term.
This here, as K to
at the very low K end.
This one, right, okay. Yeah. So this one, I don't have it in my formalism, sorry about that. This formalism, it's only describing this rise up here and this plateau. Now, these functions here that I consider constants, when I evaluate them, when I evaluate it up to super horizon scales, this X is much smaller than 1, and they become scale dependent. And the scale dependence they give rise to is this infrared tail as K to the 3.
Okay.
So sorry that I didn't understand your question inside. So essentially, once you want to evaluate your background at super horizon scales, assuming the standard formula of energy density of gravitational waves makes sense, which it's an extrapolation, these constants are not constants anymore, and they become scale dependent. And this would give rise to this K to the 3 shape I put here. Yeah.
Okay, thanks.
Yeah, thanks, Robert, for the question. And for the case of standard loops, any of these curves is a superposition of the 3 contributions, the production from loops radiating during radiation domination, loops produced during radiation domination but radiating during matter domination, this is typically the peak, and loops radiating during matter domination, which is typically given this infrared slope. Yeah. So it's different from the other argument, but this is what comes out from summing up the 3 contributions from the loop distributions. Yeah.
Yeah, Sergey, can you unmute and ask the question?
Hello, can you hear me?
Yes, yes.
Great. First of all, thank you very much for the lectures. They were really, really wonderful. I wanted to ask you if you could expand on something that you had to skip, which is the enhanced gravitational waves that come from modifying gravity. If you could expand a bit on that. But
yes,
it helped us now. So maybe they wanted to leave it for the tutorial session. I don't know.
Yes, I think I was going to propose that because I'm going to have half an hour for lunch. So why don't we stop it here? I have my lunch and we reconvene in half an hour. And if you want, we start with your question again.
Yeah, that sounds good. Yeah.
Sounds good?
Mm-hmm.
Sriram, is that fine with you?
Yeah, absolutely. Okay. Absolutely.
Okay, very good.
Okay.
Then thank you very much, guys. I'll see you in 30 minutes.
Yeah, thank you for the lectures, Danny. We see you, everyone.
My pleasure.
In,
see you now. See you now in a moment. Yeah.